In the early days of digital computing, programmers faced a relentless and unforgiving barrier: physical memory. During the 1950s and 1960s, computers possessed only a minuscule fraction of the random access memory we enjoy today. Programs had to fit entirely within these tight physical limits, forcing developers to write incredibly complex overlay structures manually. If a program grew too large, it simply crashed or could not run at all. This bottleneck choked innovation and prevented software from tackling complex, real-world tasks. Software developers spent more time managing memory allocation. The solution arrived from the University of Manchester in 1959 with the development of the Atlas computer. Researchers pioneered a concept called virtual memory, decoupling a program's view of memory from the physical reality of random access memory chips. Instead of accessing physical memory addresses directly, programs were given a private, continuous space of virtual addresses. The operating system, in tandem with specialized hardware called the Memory Management Unit, took on the task of dynamically translating these virtual addresses to actual physical locations. To the application, it seemed as though it had a vast, uninterrupted expanse of memory all to itself. At the heart of this memory illusion lies a fundamental technique known as paging. The operating system divides virtual memory into fixed-size blocks called pages, typically measuring 4 kilobytes in size. Physical memory is similarly carved into corresponding blocks called page frames. When a program requests data, the system maps virtual pages to physical frames using a specialized data structure called a page table. But what happens when physical random access memory runs completely out of space? The operating system employs a brilliant life hack. It temporarily writes inactive pages onto the secondary storage drive, a process known as swapping or paging out. When the program needs, translating virtual addresses to physical addresses for every single memory access sounds incredibly slow, and without optimization, it would be. If the system had to look up addresses in page tables stored in main memory every time, performance would plummet by 50% or more. To solve this speed bottleneck, hardware engineers created a specialized, high-speed hardware cache built. While virtual memory is incredibly powerful, it is not a magic wand without consequences. When a program attempts to access a virtual page that is not currently loaded in physical random access memory, a hardware interrupt called a page fault occurs. The operating system must stop execution, fetch the missing page from the slow secondary storage drive, load it into physical memory, and then resume execution. A few page faults are normal, but if your system runs low on physical memory, a catastrophic phenomenon known as thrashing can occur. This happens when the operating system spends nearly 100% of its time swapping pages in and out of storage, leaving zero capacity for actual processing. For software engineers, understanding virtual memory is the ultimate optimization life hack. You can write significantly faster code simply by respecting how memory pages and hardware caches behave. The most critical tip is to maximize spatial and temporal locality. When writing loops that process multidimensional arrays, always traverse them in row major order rather than column major order. Because memory is allocated sequentially, row major traversal ensures you access data stored close together on the same page, preventing frequent. As we look to the future, the scale of data processing continues to expand exponentially, pushing the boundaries of classic virtual memory architecture. Modern operating systems and cloud environments now support huge pages, which increase the standard page size from 4 kilobytes to 2 megabytes or even 1 gigabyte. This drastically reduces the size of page tables and minimizes translation.